my research at the intersection of artificial intelligence and robotics. So I focus on robot learning and perception in particular. So in layman's term, I teach robots to see and act in the real world. So in today's talk, I'd like to talk about some of my recent work on building general purpose robot autonomy. So this is, of course, a very ambitious research goal and long-term research agenda. So, but I believe that this is a truly fascinating and emerging field that will invite a lot of fundamental research in the future. So throughout this talk, I'd like to share some of my recent works that illustrates a progressive research roadmap toward this holy grail goal of general purpose robot autonomy. Okay, so let's get started. As I'm giving this talk virtually, it's due to this COVID-19 situation, and I'd like to start with it. So at this moment, it's probably still very hard for us to predict how the pandemic will lead to fundamental changes on humanity. But there's one thing for sure, that is the pandemic is already creating a real world battleground for cutting edge technology in robotics. So on one side, we have seen some successful applications of mobile robots for autonomous monitoring and disinfection. And beyond hospitals, we even see robots in natural environment, like the Spot robot dog from Boston Dynamics has been put on patrol to ensure social distancing in Singapore. But on the other side, it would be so much nicer if we could protect our doctors and nurses on the front line by turning over more and more high-risk jobs to robots. But we saw in practice that a lot of these human tasks that will require fine-grained motor skill and cognitive reasoning, especially in the medical domain, are still far beyond reach of today's AI and robotics technology. But this is not by no means the first time that we see robots get deployed to real-world tasks. We have seen this kind of giant cost-built and expensive machines running in factories and in manufacturing domains. So these are robots that are pre-programmed to perform specific tasks in well-controlled environment. And we call this the traditional form of automation that has been existing for decades. But recently, there has been a lot of amazing and tremendous progress in developing general purpose robot hardware. So as I shown in this video, so these are the more affordable and lightweight robot platforms that can be operated to perform a wide range of tasks in human environment. But so far, as you can see in this video, that most of these robots still needs a human pilot to control them. So there's not much autonomy in there. So I believe, but to truly unleash the power of this type of robot hardware, we need to think about how to endow and build autonomy and intelligence to this hardware. So much of my research has centered around this overarching goal of building general purpose robot autonomy using robot learning and robot perception methods. And I envision this type of intelligent and general purpose robots to become our future friends and assistants and companions. So their existence is not to replace us, but to enrich us in both our cognitive and physical capability. So when I think about the overarching goal of AI, I'd like to think about the reverse of these two letters, IA, that is intelligence augmentation. So the goal of building this robot intelligence is really ultimately to enrich us as a human intelligence. But to come up with a concrete research agenda toward this goal, let's begin with a contrast on what we have and what we want. So in the traditional form of automation, it starts with this custom-built machines, like I show here, and it requires a human expert that come in-house into the factories and stay with the robot for several months or even years effort and doing programming the robots for system integration. And at the end, these are robots specialized to particular type of task or behavior, like see here, making cars. And in the new form of autonomy that we are pushing towards, and now we have this general purpose robot hardwares, and what we eventually want is to enable them to perform a wide range of tasks in all kinds of different environments. So it is clear that this traditional form of system integration will not scale. So we will have to develop a new approach. What's missing here? Well, one of the major challenge, I argue, is that the kind of environment we're dealing with is unstructured. And by unstructured, I mean that there's no perfect knowledge about the world, and we cannot assume the robot's actions are always successful. So that means the robot have to constantly adapt to new environment and new situations, and also it have to constantly actively seek new information from the environment for decision making. And this challenge of the unstructured environment make it necessary for us to think about how can we endow the robot with the capacity of machine learning and machine perception. So in my talk today, I argue that to be able to move toward the North Star, that is the ultimate goal of building intelligence for general purpose robots, we will need to tackle the challenge of machine learning and perception at different level of abstraction, from the primitive motor skills to high-level task understanding, and all the way to enable robots to learn in a more human-like way. And I will motivate this research roadmap by zooming in each of the levels one by one, individually. So I will start with this low-level primitive motor skills, such as grasping, reaching, stacking. So these are the kind of fundamental building blocks of behaviors that we as humans do on a day-to-day basis. And I will describe how can we learn a closed-loop robot motor skills from high-dimensional raw sensory data from vision and touch. And this type of primitive motor skills are also essential building blocks for more sophisticated robotic behaviors. And once we have this fundamental building blocks, and this leads to the second part of the talk, that I will see how can we piece them together so that we can scale up robot learning to more complex long horizon tasks. And the third and last, and I will also talk about what are the key ingredients to enable robots to learn constantly and actively and to acquire new knowledge and new skills in the physical world to enable them essentially to learn in a more human-like way. Okay, so let's start with the primitive skill. So this primitive skills such as reaching, grasping, stacking, as I said, so they are fundamental building blocks of human motor behaviors. So they start to emerge in the very early stage of baby's motor development, where they try to stretch their arms and legs and they learn how to coordinate their perception and action together to interact with the environment. And we know that we as humans make contact with the physical world through a vast array of sensory modality, such as our touch, our vision, taste, sound. So we as humans have this inherent ability to integrate different sensory modality together for decision making. And our goal here for robots is to learn such a similar mapping from the raw perception, raw sensory data of the robot, such as like the vision from camera and touch from the touch sensors to some control command that drive the motion of the robot. And these primitives, as I said, are also essential building blocks for robotic behaviors. And we'll see how can we learn these building blocks here. So let's take an example of plugging a charger into a wallet. So we need certain amount of information from the environment and to plan our actions. Some of the information will come from vision, such as like the position and the pose of the plug and the geometry and the shape of the hole. And some other information will come from touch. For example, the forces we are applying to the environment or the friction of the plug against the wall. And based on this information, we can come up with the action to complete the task, say inserting the plug successfully. But when we take a different but similar task, say opening a lock with a key, and we want to reuse some of the task relevant information to learn a new policy. And for the uninitiated, a policy is a mapping from the sensory data to the action to control the robot here. So in other words, and so there are some amount of task relevant information that can transfer and share across tasks and generalize to new tasks. So the question is, how can we learn this representation of this task relevant information that can be shared and transferred across different manipulation tasks? So we studied this problem of learning representation using a classic pack insertion task as an experimental ground. So here in this task, and the robot perceived the raw RGB image from a camera, the force reading from a force torque sensor and the end-effector position and velocity from the robot state. And we combine the robot using a closed-loop operational space controller. So to learn a mapping from the raw sensory data to this task-relevant high-quality representation is not a trivial task. So there's multiple challenges here, and I want to highlight two of them. The first, the kind of high-dimensional data we are getting from the raw sensors, they are typically noisy and multimodal. So it requires us to develop some customized computational tools and neural network modules to be able to process this data. And the second is getting the ground truth labels to annotate and to train this representation with supervised learning can also be difficult because manual annotations can be expensive, and in many cases, we don't even know what to annotate for to be able to capture such task-relevant information. So to tackle these two challenges, our key idea is to propose a scalable approach so that we can learn a representation without any manual annotation. So our key idea is to use self-supervised learning to learn representations from the raw sensory data directly. So I will explain what does it mean by self-supervised learning. So the idea of self-supervision is directly inspired by how babies develop their sensory motor skill by actively playing and exploring the physical world, and usually without their parents, and they can figure out how it works. So they leverage their self-exploratory experiences to make sense of the world without an explicit teacher. So similarly, we here let the robot take random actions and to explore the workspace and collect data by themselves. So we can develop a predictive encoding methods that can learn the representation from the data collected from the robot's self-exploration in the workspace. So to operationalize this idea, and the key insight to train the model for the representation is to be able to predict the future outcome of actions. And by doing so, the representation can capture the task-relevant information about the system dynamics, which is essential for performing context manipulation tasks. So given a representation to the robot action, the model predicts the action conditional optical flow, the future contact, and the modality alignment. So these are the three self-supervised tasks that where all the labels can be obtained automatically from the self-supervision, and it doesn't require any human annotation. So this type of self-supervision can substantially reduce the amount of the cost of representation learning because it doesn't rely on any offline manual annotation. So using this representation learning methods, and once we finish learning the representation model, we can freeze the weight of our representation encoders and take that representation out as an input to some off-the-shelf policy learning methods. So this method separates the policy learning from the representation learning, and this separation is essential to make the policy learning a lot more sample efficient, because now we only need to train a very shallow model of 15K parameters during the online robot training, which only constitute 3% of all the entire model parameters. And this level of sample efficiency allows us to train our policy directly on the real robot. So we show that after 5 hours of training, we can obtain a robust policy for pack insertion. And this is much more sample efficient than most of the end-to-end deep reinforcement learning method that usually takes days or even weeks to learn such a policy end-to-end from the high-dimensional input. And we show that we can reproduce our result on different pack geometries with task success ranging from 71% to 92%, depends on the kind of the tolerance of the pack and the different geometries. And not only our method can efficiently learn a policy from this multi-model representation, and our policy is also robust against external perturbations and noises to the sensors. So this is showing one of the main collaborator, Michelle Lee, in the experiment where she tried to tap the force torque sensors and in order to trick the robot into thinking that it's already making contact with the box. And so using this multimodal representation, we found that the policy still be able to recover from this external perturbation and noises and to be able to perform this task successfully. But as I said earlier, and the goal of learning this primitive skill is to learn a diverse set of skills eventually as a building blocks for robotic behaviors. So to achieve this goal, and it will really speed up the policy learning if we can find that our model generalizes across tasks or skills. And we want to test on how well our model or our representation generalize. So we see that when we roll out our policy that train on the triangle pack and directly on a new square pack, so there's a significant drop on the success rate by 30%. So this is a quite big drop, and it supports what have been shown in many of the prior deep reinforcement learning work, that the policy train in one domain or one task, and they typically don't generalize well to new tasks. But when we take the representation train on the triangle pack and train on the new policy for the new square pack on top of that representation, and after again 5 hour new training, we can again recover the 92% success rate on the square pack. So this suggests that even though the policy do not generalize well to new tasks, our multimodal representation can transfer very well to new task instances. So just to give you a quick summary of the self-supervised learning methods for primitive skills, and the models first start with a self-exploration stage, where we let the robot explore the workspace and we collect the self-labeled data by letting the robot explore through random actions, which takes about 90 minutes to collect 100K data points as a training set. And once we have the training set, we can learn the representation using our model, which takes about 24 hours on a GPU, but this is done completely offline without the robot time. And after we learn the representation, now we can plug in off-the-shelf deep reinforcement learning methods, and we can learn the new policy from the representation that only takes 5 hours of the real robot time to get a robust policy. So we see from this work that self-supervised learning is a very powerful tool that allows us to process this high-dimensional sensory data without manual labeling, and it allows us to achieve that kind of sample efficiency to train these primitive skills on real robots. And the model learns the sensory representation by predicting the future outcome of actions. And this paradigm decouples the learning of the entire primitive skills into a 2 separate stages. The first, it learns the mapping from the raw sensory data to the sensory representation, as you show here. And second, once we have the representation, it learns the mapping from the sensory representation to the control policy. And this part is done by either imitation learning or reinforcement learning. But one caveat of this decoupling is that the downstream manipulation tasks do not have any say, and they do not have any impact on what kind of representation to be learned. So for this reason, we have to carefully design our self-supervised learning tasks so that we can make sure that the representation capture the important information for the downstream task. So after this work, we're asking ourselves a following up question. Can we improve this paradigm so that the downstream task can inform the learning of the representation to capture the task relevant information? And we studied this problem in the context of vision-based tool manipulation. And in this task, we assume that there's a tool object lying on the table, and the robot perceives the workspace through its RGBD camera. And from this RGBD perception, it decides where to grasp and how to use the grasp tools to interact with the environment. And here I'm showing examples of like picking up a hammer and hitting a nail, for example. And similar to previous primitive skill work that I just talked about, and we want to learn a policy that maps the visual observations to the motor command. And to deal with this high-dimensional visual data, we'll first need to learn some representations of this sensory data and then learn the controller that maps the representation to control. So one straightforward approach to operationalize this idea is to leverage just the representational power of deep neural networks to learn some latent representation. So this is the approach that we took in one of our previous work 2 years ago, where we proposed an encoder-decoder architecture, where we first used a convolutional encoders to map the image observations to some latent features. And once we have the latent feature, we can decode the corresponding action or plans from the latent representation. So this is quite a black box approach where the feature learned here are still quite high dimensional and they're not human interpretable because it's in a latent space. So there's no easy way for us to debug the system if something gone wrong. And we don't really understand how can we improve the performance once we train the model. But in many robotics domains, then we do have a quite good amount of prior knowledge about the task or the environment dynamics. So if we have this kind of knowledge, why don't we use that? And they can actually serve a very strong inductive biases and the multipliers for us to develop better representation. And in this work, we explore keypoint representation, which are compact, informative, and also, meanwhile, human interpretable. So this is a new work that we recently published in eQual 2020. So in this work, KETO stands for Keypoint Representation for Tool Manipulation. And we propose to represent a tool using 3 points. The first is a grasp point, which specifies the center of the grasp, the object used to pick up the object. And then the functional point, which is the part of an object that will make contact with the other objects in the manipulation process. And the third is the effect key point, which specifies the desired motion of the objects in order to achieve the manipulation goal. And using this key point representation, and we can specify a set of conditions that has to be satisfied in order to achieve a task. So let's take hammering, for example, and we want to be able to hammer the nail into the wall, and we want the hammer head to make contact with the nail first. And then we want the motion of the hammer head should align with the direction of the nail so that we can exert the most force. So by writing these conditions using these analytic equations, it allows us to turn the motion generation and action prediction problem into a constraint optimization. So for this task, we are considering such as hammering, reaching, pushing, and we show that we can formulate this optimization as QP, quadratic programming, which can be solved very efficiently using numerical solvers. Okay, so once we have this formulation, this is our model pipeline. So at the beginning of training, we use a key point generator to generate a bunch of key point candidates. And we evaluate this different key point candidates by executing them and evaluating in a physical simulator. And as expected, some of the key point combinations will lead to success. There's a successful completion of the task, and some of them will lead to failure. And using the success and failure combination, it will give us a set of a training set of a positive and negative key point combinations. And we can incrementally add these different samples to a growing set of training data and use this data set to train the key point generator. So to draw an analogy to the packet insertion work that I just talked about, and the key point generator here is a representation module that maps the RGBD perception of the robot to the structured key point representation. And the action optimizer is a policy module that maps representation to the action commands. But the key difference here is the policy iteratively generating new training points to update the representation. And by doing so, this way, it allows the representation, key point representation to be learned from interaction for interaction. Okay, so to show some qualitative results and coming out of this formulation, we showed here there's the visualization of our learned key point and the policy for different manipulation tasks. And this is showing example of a hammering task. And this is showing another example of reaching an object in a thin tunnel. And you can see based on the different task objective, different key point representation emerge from the same hammering objects. So the robot learns to use the same object in different ways to achieve different task goals. And quantitatively, we found that using our key point representation as an intermediate representation, and it leads to significantly better generalization to novel objects compared to the latent features that we use with end-to-end trained deep neural networks. So now we talk about given a tool and how to make best prediction to make the best use of the tool for a manipulation task. And we want to take a more ambitious goal to consider the inverse problem. Can we create a new tools and given a task to be able to solve this task? And this is becoming a more popular task in the robotic community, sometimes referred to as MacGyvering, which means using items in a creative and often unusual way for inventive problem solving. And we show that using this structured key point representation, and they can serve an informative scaffold and in creating such tools from different object parts. And this is done by fixing the key point representation and do backward optimization to find the best combination for object parts that give you the highest score for this key point representation. And this video demonstrates that created tools and that can successfully complete a task, and it showed that an example where the model creates a new hammer by combining a screwdriver and a wrench together. So to summarize this first part of the talk, I first introduced a new learning paradigm for primitive skills based on the idea of self-supervised learning. And it allows a robot to learn the representation from a random play of self-exploration of the robot in the workspace and without manual annotations for the training data. And it learns the primitive skills with minimal human supervision with a very efficient, like a 5-hour training on the real robot time. And I then talk about how can we use the downstream task to supply feedback to the representation module. And in case we have the prior knowledge about the domain and the task, and how can we leverage them as a structured part that can give rise more compact and more informative representation for manipulation. So after this first part, and we now have this diverse set of building blocks and for the primitive skills. And this leads to the second part of the talk. How can we use these building blocks to compose for more complex long horizon tasks? And our observation here is for a lot of this real world tasks, such as driving or cooking, and that we as humans do in a day-to-day basis, they usually follow a compositional structure. And by that, I mean that a complex task can be hierarchically and gradually decomposed into smaller and more fine-grained subtasks. So in the last part, I talk about how can we use self-supervised learning to learn a repertoire of primitive skills. So in this part, I will talk about how can we kind of piece them together to build more sophisticated robotic behavior for this, to tackle this long horizon task. And for this task, we can no longer use a simple sequential composition of primitive skills because the complexity grows exponentially as the task length gets longer and longer. So we need a way to reduce the problem size so that we can divide and conquer. So as I said, like, so one of our key observations is like those tasks usually have like compositional structure. So we want to build models that can harness this compositional hierarchy and abstraction and in this long horizon task so that we can reduce the problem complexity. So to motivate our approach, and let me just give you first a very intuitive example of making this beautiful 3-layer cake. So when we as humans make such plans on how to bake this cake, we might first think about the high-level milestones. Like for example, we first need to build this base, the first step, and then construct the second layer, and finally stack the top layer. And so these are the intermediate subgoals that we have to reach in order to make this cake. But after we make the plans for the milestones, we can now think about the low-level actions and how do we achieve those milestone goals. I'm not a baking expert, but you kind of get this idea. And inspired by this type of thinking, and we developed a new hierarchical planning module called Regression Planning Network. So this model takes the current observation and the task goal as input, and it determines what is the next immediate subgoal to reach. And the task goal here are specified by some symbolic expression for like putting the pot on the stove. And you can think that them as some kind of specifications of the milestone goal that I talked about using the cake example. So our model is directly inspired by two parallel lines of research. So the one is the symbolic planner used in classic AI literature. So they have been shown very effective in long horizon reasoning, and they usually abstract away the perception side with symbols and planning domains. So that's the kind of main limitation of this type of model. And the other thread of research is a recent work on using deep learning to plan from raw observation. And these models can directly operate with raw sensory data, but they usually only work well for short horizon tasks. So our goal here is to combine the best of both worlds. So the key idea of our model is to plan backward in the symbolic space, conditioning on the raw visual observation. So this allows us to plan with raw sensory input and meanwhile scaling up to long horizon tasks. So the regression planning process is to apply the model recursively by feeding the predicted goal back to the model until a predicted goal is reachable from the current observation. And by reachable, that I mean that the current milestone goal can be achieved by one single primitive skill. So the model first takes the final task goal and the current observation as input and predict what is the subgoals that have to be done in order to reach the final goal. And then we use a reachability network to determine if this subgoal is reachable or not. And the reachability network predicts no here. So that means we have to divide even further, and we have to plan backward to get like a reachable subgoal. So in the next step, we feed the predicted goal from the last step to the model again. And the reachability model still says no. That means this subgoal is still out of reach from the current state by a single primitive skill. And so this process goes on and on until we arrive at a subgoal that can be directly reachable. Now the reachability network says yes. So until here, we can stop planning and execute the corresponding primitive skill controller. And this controller tries to reach the subgoal from the current state. And after the skill execution is done, we can then repeat the regression planning process until all the way we reach the final task goal. So to show you some kind of qualitative results on this regression planning module, we train our model on a set of video demonstration on a simple and idealistic cooking task with 3 ingredients and 2 dishes. And this video shows an example of a test time execution of a longer cooking task with 3 dishes and 4 ingredients. And compared to prior work that tries to learn to plan from raw observation, we show that our RPE model can achieve very strong generalization, almost close to 100% success rate on same tasks of different lengths. And it also have the capability to extrapolate from a shorter training task to longer test tasks, and due to this symbolic abstraction and regression planning mechanism. So to have a concise summary of this RPE model, so the core idea here is to use regression planning technique so that we can recursively plan backward on the symbolic subgoal. And the method works well on visual input without specifying a planning domain. And our model can learn from a set of video demonstration and achieve zero-shot generalization to new tasks and also longer tasks. However, one of the key limitation of this work is that we kind of model the low-level primitive skills as predefined API calls. So we assume that there's a bag of APIs that as a primitive skills we can choose from, and then we only predict which one to execute. So these skills are predefined and invoked once the model determines what is the next subgoal. So when there's something wrong with the low-level skill and the low-level execution fails, the high-level planner doesn't know what to do. And this is not just a problem to our model, and this is, to me, one of the million-dollar question in such kind of a hierarchical abstraction and modeling. Like, how can we have this low-level primitive skill and high-level task plan inform each other, and what is the best way that we can learn and predict this primitive skill and task plans altogether? So to address this problem, and we study it in a multi-step robotic manipulation task shown in this figure. The robot is asked to move the target object to the goal position by pushing it with a stick. So the target object is required to move across the grid tile step by step towards the goal. And if the target leaves the grid tile, and we consider this as a failure. And we can imagine this grid tiles as some kind of environment constraints in realistic robotic manipulation tasks. And so this is a quite long horizon task, and it becomes even more interesting and challenging when there's multiple objects placed on the table. For example, when there's a presence of an obstacle, and the robot have to first move away the obstacle, so that now once the path is clear, the robot will be able to push the target objects to the goal location. So one of the common techniques to address this long horizon robotic manipulation task is model-based learning. So the core idea is to learn some kind of forward or inverse model that has some predictive power. So the key idea is to learn a forward model that's used to predict the resultant states given a sample action. So these are the outcome of these actions. Once we have this type of predictive model, the optimal action sequences can be selected by unrolling the dynamics model and try different action combinations, and so that we can find the action sequence that leads us to the goal. However, in our environment and our long horizon task, planning directly with visual observation and the continued action space can be very inefficient. That's because most of these randomly sampled actions they do not make meaningful changes to the environment, and because most of them are distant from the object or they violate some environment constraint. In this long horizon task like ours, and the search space of possible plans will also increase exponentially. So the chance of finding a plausible and effective long horizon plan directly from the action space can be very slim. And in addition, we consider all possible actions when forming a plan. It means that the forward dynamics model have to learn all the consequences of all possible interactions. This will also make the computation intractable for long horizon on complex tasks. So our idea is to prioritize more promising action samples so that we can plan with those and only prioritize sample those more promising actions that will make meaningful change to the environment. And to operationalize this idea, we perform planning in a learned latent space instead. And here we use an action generator, and that can be learned to approximate the distribution of promising actions conditional on the current state. And in this way, we can obtain a plausible action by sampling from the latent space. But however, existing methods and using this latent space planning, they only use and make use of flat plan. So as a result, this method mostly focuses on very short horizon tasks. So we still suffer from the exponential blow up of the long horizon planning problem. So following the same intuition using the prior work, we propose to factorize the planning process into two-stage approach into the task, milestone goals, and the primitive skills. And we develop a hierarchical planner called Kevin. So our Kevin planner hierarchically generates plans in a learned latent space of sub-goals and skills. So first, we perform high-level planning by select the desired sub-goals to reach in order to accomplish the task. And once we have the sequence of high-level goals, and we then plan for the low-level actions to select the desired primitive skills in order to fulfill this chosen sub-goal. And the distribution of the reachable sub-goal at each step depends on the physical property and their spatial arrangement of all the objects. So for the high-level plan, we introduce a metadynamics model to be able to capture the distribution over the sub-goals. So it is implemented as a deep generative model that maps a latent code C to some reachable sub-goal in the future, conditional on the current state. And we predict this accumulative reward of each sequence of sub-goals so that we can choose the next immediate sub-goal that leads to, most likely leads to the final task goal. And for the low-level plan, we introduced an action generator that used both the latent code C and Z, and it captured the distribution of possible actions. And conditional on the current state and the latent code for subgoal C, and the action generator maps the skill code Z to a plausible action sequence that will push the object toward the next subgoal. And finally, we use a low-level dynamics model to evaluate this generated action sequence. The best action sequence will be selected and executed on the robot. So the model is trained on task-agnostic interaction in the simulator. So we also follow the same idea that we let the robot explore the workspace by issuing random pushing actions and on the table without any task reward. So this allows us to train these two dynamics models together, both the metadynamics model and the action generator. So we develop a cascade version of inference algorithm to learn both modules together. And these two inference modules on the bottom, like shown by QH and QG here, are used to infer the latent code of subgoal and primitive skills. We derive a variational lower bound objective to train both modules jointly. So qualitatively, we show that for this long horizon strategies emerge from auto training that the robot is able to move away the obstacles to make way for the target objects to reach the goal location. And quantitatively, we show that our model significantly outperforms the baseline models that do not use this hierarchical factorization of subgoal and primitive skills, as well as other baselines that do not learn the high-level plan and low-level skills together. So this concludes the second part of this talk, which I focus on how can we combine this primitive skills as building blocks to perform long horizon tasks. And our idea here is hierarchical abstraction and factorization of the high-level plan and low-level skill. And we show in regression planning network this high-level plan can be represented by symbolic abstraction to achieve strong generalization. And in the Kevin work, we demonstrate that this high-level plan and low-level skill can be learned together from task-agnostic interaction. And for this reason, and for this as a result, we can demonstrate that this leads to a higher performance and strong robustness at test time. Okay, so now I conclude the first two sessions and how do we learn the primitive skill and how do we use them for long horizon tasks. But remember that our North Star goal is to achieve general purpose robot autonomy in the wild, in the physical environment, like we as humans are living, and where the robot have to constantly adapt to new situations and new tasks. So I argue that the last piece of the puzzle toward this high-level goal is to enable robots to learn in a more human-like way. And by human-like, what do I mean here? So the majority of work in robot learning literature so far has focused on learning in closed world domains for specific tasks. So this is quite different from how we as humans learn fundamentally. So we as humans are embodied, active, and environmentally situated creature. So we learn from our day-to-day interaction with the world and with other agents and gradually build a model of the world. So that learning doesn't really happen in one shot. It is a lifelong learning process of active exploration and model building. And this lifelong learning mechanism is essential step towards general purpose robot autonomy. And as a robotic researcher, and the more I work on robot intelligence, and the more I got to appreciate the richness and depth of human intelligence. And today, robot intelligence is still quite narrow-minded, and they find one solution and to solve a problem, and they usually stick with it. And by contrast, humans are really good at reading at like creative ways to solve a problem, and they have this kind of extraordinary dexterity to physically manipulate the objects to achieve this goal. So to endow the robot with this level of cognitive and physical reasoning capability, the robot have to first learn from human ingenuity. For this purpose, we developed a robot Turk, so a cloud-based crowdsourcing platform for large-scale human demonstration collection. RobotTurk allows users to connect to a remote robot from a cloud server, and so that they can move their phone in free space and control and teleoperate the robot in the factory in 6 degrees of freedom. And with this system, we deploy the RobotTurk on a set of physical robots to collect real-world demonstration of challenging robot manipulation tasks, such as like sorting objects from a bin and putting them into corresponding bins, arranging a bunch of kitchenwares, and also folding laundries as my favorite task. And we show that in one of these tasks, and we ask people to stack a tower with a set of cups and bowls on a tabletop. We're just amazed by the kind of emerging strategy coming out of this human demonstration. Some notable example includes alternating the cups and bowls and to try to reach as high as possible. And some human demonstrators then decide to flip the bow to create a stable base. And this is quite amazing because we don't even know that is possible a priori. And some other human demonstrator and then put 3 cups together to make a stable platform so that they can stack other objects on top of that. So as you can see that this is a quite diverse and rich data set coming from human demonstration. So to facilitate robot learning research, and we have make this data set to the public. So our human demonstration data set is by far the largest robot manipulation data set through teleoperation. This data set, I believe, opens the door to many interesting projects on how to learn from human ingenuity for robot intelligence. We have been working on a variety of topics using the RobotTurk dataset, such as policy learning, video prediction, and task planning. And I will be excited to see how the community will be able to use this dataset for their own research. And not only we want models that can learn from human, and eventually the robot also needs to learn like a human by themselves. So I argue that there are 3 key ingredients that we should collectively work on to be able to make robots to learn in a more human-like way by themselves. So this includes learning to learn, so the ability to reuse prior knowledge to learn and adapt faster, and causal understanding, and the ability to understand and reason about the cause and effect of the interactions. This allows us to generalize to new situations. And also, of course, compositionality, as I talked about in the second session, that trying to capture the compositional structure of semantics and tasks so that we can better reuse prior experiences and reduce the task complexity in long, hard, and complex tasks. So in the last few minutes, and I just want to give you a very quick show and tell on some of our latest efforts on these 3 directions. So for learning to learn, and we investigate a meta-reinforcement learning method that can quickly adapt behaviors to new tasks. So the core idea is to learn a latent space of task embedding where each task can be represented by a vector in this latent space. And we can then perform online task inference by having agent interact with the environment and collect some experiences as context. And using this context, then we can infer the task identity. So to make the online task inference more effective, we propose to factorize this latent code into a global and local context, where the global context represents a mixture of subtasks, that is a collection of primitive skills the robot needs to do for this task. And the local context captures the transition between the subtasks. So we show that our online task inference method is exceptionally effective for long horizon tasks that will involve a sequence of primitive skills due to the factorization of the global and local context. So for causal understanding, and we develop a new causal inference method that allows the agent to interact with the environment and collect experiences so that it can build a causal model from their own experiences. And then using this causal model, and we can develop a goal conditional policy that can harness the causal knowledge embedded in the causal model so that it can effectively generalize its behavior to new tasks and to new environment with different and novel causal structures. And our experiment demonstrated that our model significantly improved the generalization of the agent in understanding the causal and cause and effects through interactions, and being able to complete and perform new tasks in new environments by using this correct understanding of causal relationship. And for compositionality, we studied the problem of learning from video demonstrations. We cast this as a meta-learning problem. The goal here is trying to understand a single shot of video demonstration and being able to instantiate a policy to perform this task. And we propose to represent a video demonstration into such a program structure that allows us to decompose a complex task such as like a sequence of block stacking into simpler pieces. And by using this hierarchical decomposition, we show that we can achieve much strong generalization to new tasks. And meanwhile, compared to flat baseline that do not harness this compositionality, we can achieve significantly better generalization with less training data. So I know that this is a very quick overview of like some of the latest effort, and I gloss over some of the technical details here, and you're welcome to ask me questions or check out the paper offline if you're interested. So to summarize this last part, I first talk about how can we learn from human, and I introduced the robotic platform that harness this human ingenuity from crowdsourcing human demonstrations. And then I talk about how can we build intelligent agent that can learn like human, and I pinpoint 3 directions that we are pushing towards to enable robot to learn in a more human-like way. And this includes the ability to learn so that we can learn faster and adapt faster to new environment and new tasks, and to reason about the cause and effects so that we can generalize to new situations better, and also to exploit the compositional structure of tasks and semantics so that we can reduce the problem size and scale to more complex tasks. So to conclude, I'd like to summarize the progressive roadmap that I outlined in today's talk towards building a more general form of robot autonomy in the world. I first start with primitive skills, where the key technique we develop here is based on the idea of self-supervised learning, which allows the agent to develop these fundamental building blocks of behaviors by self-exploration and interaction. Then I talk about how can we compose these skills together to solve long horizon planning tasks through hierarchy and also symbolic abstraction. Finally, I pinpoint a few directions on how to build intelligent agents that can learn more efficiently and effectively through the idea of causality, learning to learn, and compositionality. And the key idea is to let the agent to learn in a gradual and iterative way through active exploration and model building. So this is a truly fascinating research field, as you can see, and I believe it leads to both a lot of fundamental theories as well as like practical applications, and with the wide accessibility of affordable robot hardware, as well as like the great advances in artificial intelligence. I think this is really the best time to work on the general purpose robot autonomy, and I believe that there's a tons of research problem waiting us to be solved. So with that, I'd like to thank all the wonderful students and collaborators and who work with me on the projects that I discussed today. Now I'm happy to take some questions.
Thank you so much, Yuke. A couple of questions did come through. The first is in reference to the first part of your talk. What motivates a better grasp point or end of the hammer handle if the goal is achieved with a less efficient grasp point or the middle of the hammer?
Yeah, so the goal here is like we want to investigate grasp and grasp the selection in a task-oriented way. So there has been a lot of work on grasping objects for stability, where the goal is to be able to lift up the object from the ground by finding the most stable grasping point. But we kind of argue that for actual manipulation tasks, if the goal is to grasp and manipulate the object of like subsequently for a purpose, only optimizing the stability is not enough, because we also need to take into account what is the affordance of the tool and what is the task goal. For example, for hammering the object, we might want to grasp the handle and then hammer the nail with the hammer head. But if we are doing like a pushing, and that will require a long and a flat part, and probably it's better to grasp the hammer head and push with the hammer handle. So based on this kind of like task goal, and really the core idea there is we want to have this kind of feedback mechanism so that the downstream manipulation task can inform the selection and choice of grasps.